Okay, so this one here is using the fundamental theorem of calculus. Now, if I were to actually try to anti-differentiate this function, I can't because I don't know what the antiderivative is. However, what I do know is whatever that antiderivative is, when I differentiate it, I get the function back. So I'm going to end up with something that looks like this, d by dx of f of x minus f of a. Well, f of a is a constant, so really I'm going to end up with the derivative of f of x, which then gives us the original f function. Okay, so that's what I'm going to use, is this notion of the fundamental theorem of calculus. Okay, so this is, if I were to write that in, that's going to be equal to the original f of x. Okay, well, that said then, this is going to just end up being log sine of x over x minus 8 square root. And that's it. Now what we have to be careful of with this is if the endpoint is a function itself, then we end up with an embedded function here. So when we do the derivative part of it, although the f of a still disappears, we need to apply chain rule. Okay, so this is an example here. So we know that, again, we can't anti-differentiate this, but we do know that, well, if I can get the antiderivative as with sine x, so it's going to look like this, d by dx of big F of sine x minus f of a. Okay, well, if that's the case, that's going to differentiate to 0. This is going to differentiate to f of x, but I need to apply the chain rule, which is the derivative of sine, which is cos x. Okay? So I just have to, because of this function here, I have to just make sure I apply the chain rule in this case. So then I'm going to end up with 1 minus t cubed, or sorry, x cubed, not x, sorry, sine cubed, because I'm going to put sine x into that function. Then I have to just remember to apply the chain rule because I had an embedded function in there. For these ones, these are improper integrals, so I'm integrating across an asymptote. So if I just sketch a quick graph of this, there's an asymptote at +1. Okay, it's going to be an asymptote going like this and like this. So if I'm integrating from -2 to 3, okay, I have two different areas here. I've got area on this side of the asymptote, and I have an area on this side of the asymptote. Oh, what happened to my, where'd it go? There it is. Okay, and I have area on this side of the asymptote. And I just have to make sure that I do those separately. Okay, so this then becomes the limit. I'll do the green part in green. So limit as a goes to 1 from the negative side. The integral of -2 to a of 3 over 1 minus x squared dx. And then plus, and although the integral is going to end up essentially being the same, okay, I'm going to do the side in blue, the limit as a goes to 1 from the positive side, because we're going to be integrating this way to the asymptote. Okay, so we're going to start on this side of the asymptote. Actually, we're not integrating that direction, but we're starting on this side of the asymptote. We're going to start at a, or 1, and go all the way to +3. And this is going to be the same function, so we should end up with the same integral. Okay, so the limits are formalities, but it's important to split this up because this is a very important issue. Okay, because if you don't split it up, you end up with all sorts of weird results. Okay, so integrating this is going to end up being the limit as a goes to 1 from the negative side. This is going to be -3 over 1 minus x times -1. Okay, so that's going to get rid of the negative. and I'm going to integrate this from -2 to a. Okay, same thing over here. This is going to be the limit as a goes to 1 from the positive side. Same integral, -3 over 1 minus x to the power, and then we have to divide by that chain rule of -1, and this one's going to be from a to 3. Okay, well, plugging it in, I can evaluate this. As we go to 1 from the positive side, so this is, I'm just going to clean this up a bit. That's going to be +3. Let's just make this a little bit easier to look at. As I go to 1 from the negative side, okay, of 1 over x, okay, so this function looks like this. I'm just going to look at, well, I'll write 3, 1. If I look at this graph, it's a vertically flipped, so a horizontally flipped graph that looks like this. Okay, and it's approaching, there's my asymptote. It's going to look like that. So as I approach 1 from this side, it's going up to positive infinity. Okay, so as I plug in 1 in here, I'm going to end up with positive infinity minus, and I'm going to plug in the 2 into here, minus 3 divided by 3 is 1. Okay, so that's the area underneath the green part. It's infinite. Plus, I'm going to do the same thing here. Okay, so I'm going to just clean this up. It's going to be equal to 3. And again, looking at this from, I'm going to plug in the 3 first, so I'm going to end up with 3 divided by -2. Okay, 3 over -2 minus, as x goes to, or a goes to 1 from the positive side, it's going from the positive side now, so it's going to be approaching the asymptote in that way. It's going to go down to -infinity, so it's going to be minus -infinity. Okay, as it approaches that positive, the 1 value from the positive side, so that's the 3 over 1 minus x function. It's going to -infinity from that side. So when I work that all out, that's just going to be infinity minus 1 plus whatever that is, plus infinity. It's going to be 2 infinities basically, where the area is infinite. This area, unbounded area, is infinite.